Hello and welcome back, everybody. Today we are looking at the error bound for the integral test. So meaning like if you use the integral test to solve for a problem, and I want to say maybe use only 5 or 6 terms in the summation of the series to estimate what is it supposed to be equal to. So I want to know what would the error be, and how accurate is my answer going to be. Now in our textbook, you'll see that they have an equation just like this over here, which tells you what is the error for using what we just said. But we're going to go ahead and go through a problem thoroughly so you can see how it's actually derived. So then that way you can kind of draw your conclusion as to why this equation came about. All right, so here in our first problem right here, what we're going to do is we're going to estimate what is the summation from n is equal to 1 all the way to infinity of e to the negative n using only the first 6 terms. So that means I'm just going to take the first 6 terms and add them up, and then I'm going to use that to estimate what is going to be supposedly the total then. So for this one, that is hopefully not too bad. So that means the first term over here is going to be e to the negative 1. Actually, let me go ahead and use red for this one just to indicate that those are going to be my answer in this case. Okay, so my answer, s of 6, because I'm using the first 6 term, is going to be equal to e to the negative 1 plus e to the negative 2 plus dot 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 all the way to the 6th term, which is e to the negative 6. Now, saving you a little bit of time, your calculator, what's going to show up is that when you plug it in, it's going to be 0.581. So that's going to be an estimate of the series using the first 6 terms. And I can do that because the terms are going to progressively get smaller and smaller and smaller. Now, hopefully you can recognize that if you use more terms, then that means that your estimate will be more accurate. But the problem is then you have to actually punch in more items into your calculator, and that could be kind of tedious. So that's why we're only using like 5 terms or 6 terms or something like that, because the terms afterwards, it might be so small that it becomes insignificant in terms of like how much you add. Now, something that you should note is that e to the negative n, this is after assuming that it passes the integral test. So that means that it has to e to the negative n also has to satisfy all these conditions over here. E to the negative n is supposed to be continuous. And then e to the negative n as n approaches towards infinity is going towards 0. And finally, e to the negative n is also monotonically decreasing. So on the right-hand side, graphically, you can see actually that's happening. And those three conditions are definitely true, and you can show it algebraically as we normally would do for an integral test. But so for right now, I'm just kind of like bypassing that just so that we can talk specifically about the error then. Okay. Now, part B, what I want to do is I want to estimate what is the error bounded from using part A. So that is to say, if I'm using only the 6 terms like there, like how close am I to the actual answer? How close am I to the actual answer? Well, if I'm only using the first 6 terms, then that means that everything afterwards would be considered as an error then, because here, the first 6 terms will be this right here, plus 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 this right here. Anything that I did not use, well, that is going to be the error because the sum of all of those partitions would give me the total of the series that it's supposed to add up to. So one would say anything beyond the 6 terms, that's going to be the error then. So now I want to go ahead and see how that works out in terms of partitions. So you can kind of estimate what the error is using an integral. Now, what we're going to do first is we're going to go ahead and set up the right-hand rule in this case for the partitions. So that means I am going to use the right-hand partitions for each one to see what the error is going to be. So over here, you can see that if I go to say a of 7, the 7th term right there, we're going to use the right-hand side to build our partition right there. And then afterward, this is going to be the next one, and then this is going to be the next one, and then this is going to be the next one, and so on, and so on, and so on. So this partition, that is going to be a of 7, because that is going to be a 7th term, right? Since it's using the height at a of 7. And then this is going to be a of 8, and then this is going to be a of 9, and then it's going to be a of 10, and so on, and so on. So all of that right there, a of 7 plus a of 8 plus a of 9 plus a of 10, and so on and so on and so on. That right there is going to be my error then, okay? Because those are all the terms that we did not use. And if you notice, in terms of an integral, that right there, since all of these partitions are under the curve of e to the negative n, then that means it should be less than the integral. Looks like it's going to be from 6 all the way to infinity of e to the negative n dn. So right there, that tells me that the error is bounded above by that integral right there, because you can see that the area under the curve is going to be greater than those partitions that are created on the right-hand side. So that's my upper bound for the error. Now, if I try to do this using the left-hand rule, so you can see how that works then, okay, then that means I'm going to go ahead and set up those partitions over here. So this one, using the left-hand rule, so a of 7 is over here, a of 8 is over here, a of 9 is over here. So here's a of 7 because you're using the seventh term as the height. And then the next one will be a of 8, and then a of 9, and so on and so on and so on. In this case, the error, which is a of 7 plus a of 8 plus a of 9 plus a of 10, and so on and so on and so on, once again, that is going to be my error because those are going to be the terms that are not going to be used. And you'll notice now, if I compare that with the integral, right, the partitions that I'm creating here are going to be overestimate because those are going to be above the area under the curve. So in terms of how big is it going to be? Well, or what is it going to be bigger than? It's going to be bigger than the integral from 7 all the way to infinity of e to the negative n dn. Because you can see, once again, those partitions afterward from 7 on, the partitions are going to be bigger than the area under the curve. So that's good because now my error is going to be bounded by something that is above over there and then something that is below. So putting it all together, then that means that the error for using 6 terms will be concluded by the following then. Okay, so the error for using only 6 terms earlier, according to what we said, is going to be bounded by above by integral from 6 to infinity of e to the negative n dn, whereas it's going to be bounded by below from 7 to infinity of e to the negative n dn. So that's going to be r of 6. And once again, r of 6 means that you're going to use only the first 6 terms to estimate what is the series, what is the sum of the series. So all the residual terms that you did not add, well, that's what it's supposed to be equivalent to. So to generalize what's going to happen over here, right, if we were to look at this as a general case, then your error that you're looking for is always going to be, well, according to our example over here, the is always going to be less than or equal to the integral from k to infinity of a of n dn, where k is the number of terms you use. And also, it's going to be greater than or equal to from k plus 1 to infinity of a of n dn. Now, if you're wondering, okay, well, all of a sudden, how come we're using less than or equal to versus just strictly less than? The reason for that is there are some cases where it's kind of like trivial, where this is still true. And that is if you do like a summation of 0. That is what we call a trivial case because we never look at that situation. But for that, but because that situation occurs, then that's why we have something that is less than or equal to in this case. Okay, but you know, if you're thinking of a of n being a function, I think 99.99999% of the time there will be no situation where the partitions would then be equal to the area under the curve then. Okay, so in my book, it really should be just strictly less than for both cases. But nonetheless, to kind of conclude that answer as to like, you know, what we're trying to find, then that means that the error, right, r of 6 in our scenario is going to be less than, and less than over here, the integral from 7 all the way to infinity. Oh, sorry, not 7 to infinity. It's going to be from 6 to infinity of e to the negative n dn. And then it's also going to be greater than 7 to infinity of e to the negative n dn. And as soon as you see this, this is where your improper integral is going to come in. So let's go ahead and take one of these guys right here and try to solve for it using improper integral. So limit as, let's say, a is approaching towards infinity of 7 all the way to a, and then we have e to the negative n dn. So taking the antiderivative, we would get the limit as a approaches towards infinity, and then we have e to the negative n and negative because it's the antiderivative, and then boundary from 7 all the way to a. plugging in your upper bound and your lower bound, you would now get limit as a approaches towards infinity of negative e to the negative a, and then we have plus e to the negative 7. So as the first term right here, that's the only one that contains a. And as a approaches towards infinity, that definitely goes to 0 because this one right here, you can look at it as 1 over e to the a with a negative in front. So you can see how that goes to 0. So all that is left is just e to the negative 7 then, and that's going to be your lower bound. Now, for the upper bound, we like to do exactly the same thing, but you can see that if I do, it's going to be exactly the same type of work as what I just showed. So it's most likely we can kind of like recycle this part over here. I like to think that the lower bound, because of the way that we just saw for it, that we said is going to be e to the negative 7. The upper bound would then be e to the negative 6, according to what we said, because that 7 came from the lower bound in this case. So the 6 would then only make sense to be on the exponents in this case. So there we go. That's going to be my error for using only 6 terms then. It's going to be somewhere between e to the negative 7 and e to the negative 6. Okay. All right. Now let's go ahead and move on to the next part. I want to know now, what is the boundary for the estimate of the entire series for using only the first 6 terms. So what I'm trying to say is, okay, now let's look at the whole series. Okay, let's look at this whole series. And I want to know, because I use only 6 terms to estimate it, what is the upper bound and the lower bound of the series? Okay, earlier in part B, we saw for the error bound. Now we're going to solve for the entire series, like how big is it maximum and how small is it going to be maximum. So that is to say, I want to know if S represents the series, what is it bounded above and below by? Well, previously in part B, we came up with this equation right here, where R of 6, which is the error for using 6 term, is supposed to be equal to this guy. Now note over here, R of 6 means that that's supposed to be the sum of all the other terms afterwards. So that means it's going to be equal to A of 7 plus A of 8 plus A of 9 plus A of 10 plus so on and so on and so on. So all the terms that's missing afterwards. What I can do is I can take this inequality and add the components that are missing to make the entire series. So that is to say, why don't we go ahead and add S of 6 to everything, okay? Add S of 6 to everything. Because if you take S of 6 and add it to the middle part right there, that right there is going to be the entire series because that's going to be all the terms. And that right there is what I'm looking for. So that now gives me S, which is the entire series, is going to be less than, and I'm going to go ahead and use less than because I know that those upper bound and lower bound are never going to be equal to. It's going to be equal to S of 6 plus the integral from 7 to infinity of e to the negative n dn, and then S of 6 over here plus the integral from 6 to infinity of e to the negative n dn. And hey, all of those we actually have numerically because we solved for it earlier. From part A, we said that S of 6, that's supposed to be somewhere between approximately 0.581, and then plus this guy right here, e to the negative 7, if I remember correctly from part B, is less than the series, and then that's going to be greater than, once again, just plug in my answer from previously, 0.581, and then plus e to the negative 6. So if I take those and add it up, then that tells me that the series, the total sum, is going to be somewhere between those numbers then. Okay? All right. So now for the very final last part over here, I want to know how many terms should I use so that my error is less than a certain amount. And let's go ahead and fill this in. Let's go ahead and say that the amount is going to be less than 0.001. Okay? So meaning like, 3 decimal places or something like that. So if I'm setting up an error, right? Okay, so let's think about what we have so far. The error that I'm looking for, right, which is denoted as R of 6, as we have said earlier, is supposedly going to have an upper bound that is going to be the integral. So then that is something that I can then replace then. So let's see. If I'm looking at the integral part, right, then that means that the integral from 6 all the way to, actually, no, I'm sorry, kind of messed up right here. So the error is going to be equal to R of n. okay, R of n, because we're no longer using 6 terms, okay? That error is supposedly going to be less than the integral from n all the way to infinity of a of n dn. Okay, so remember the upper bound of the error is going to be less than the integral from n to infinity of all of that stuff right there. And I want that guy to be less than 0.001 because remember, I want my error to be less than that. So if you think about it as like an inequality, if this guy is greater than this guy, then it's definitely going to be this guy is greater than this guy right here. Okay. Well, everything that I have right there is solvable because, well, we have everything all set up. So let me go ahead and say the number of terms is going to be, let's not use n in this case because I'm already using n as a variable right here. Let's just go ahead and say the number of terms will be k in this case. Okay, so k number of terms will give me an error that's less than 0.001. So limit as k, sorry, not k, limit as a is approaching towards infinity of the integral from k to a of e to the negative n dn is going to be less than 0.001. And just like before in the previous parts, we can use the antiderivative to solve for this improper integral. The setup would then give me, after the antiderivative, is e to the negative k is going to be less than 0.001, just to save a little bit of time because, you know, all that work is going to be the same thing. Now I need to solve for what k is equal to. So we're probably going to have to take the ln of both sides. So we're going to have negative k is less than ln of 0.001, which is equal to approximately ln of 0.001. That is going to be equal to negative 6.908. Okay, and then finally, if I want to solve for k, then divide by negative. So k has to be greater than 6.908 then. So then that means in conclusion, after the seventh term, okay, then you should have an accuracy that is going to give you something that is less than 0.001 then. Okay. All right. So there it is. Thank you so much for watching. I will see you guys next time. Goodbye.